It's not the problem of normalizing it that I know of. If you don't, it should work if you normalize it. Not there's an issue with that. But you can also do it validly because the eigenvector is supposed to drop out of
Do anything?
and so you can just say, in the case of the normalized eigenvector, you don't have to go through all the calculations or everything. You can just say, my normalized eigenvector is the eigenvector belonging to Jm. Right? Kind of like the ket Jm, right? JML.
Good.
Cooked all Thanksgiving and all that. Jm. You can just say, my whatever eigenvector I have corresponds to this. And then you go through with it, and it's self-normalizing to do that.
Okay.
So like basically, right here, for the expectation value of Jz, I just say it's Jm, which then we know that Jz times Jm is equal to itself. And then you can do that for Jz squared. It's just that twice. It's equal to h bar squared, and you get 0.
Okay.
Which makes sense because spin is only happening at 2 dimensions,
Yeah.
right? So a third dimension can be determined.
Jacob looks not okay with this, huh? Oh, I don't know. Okay. I'm here. You're okay? Good morning.
Only people who are not okay offer that.
Fair.
Talking to someone, I'm okay. That wasn't a question. Are you good?
I'm good, it's fine, don't worry about it.
Fine.
In this solve the problem, this is this associated linear differential equation, right? The solution. So the solution is associated. So this P(x) is a half. That is the Legendre polynomial. Those order of Legendre polynomial, which is okay, I think we end up here, so now we can keep continuing. Today we are going to finish this discussion and do one example if we have time. The property, there's a one property that happened in textbook, so I'm going to properties of L and X. X is cosine, right? First one, this one, if m is negative m, L, that equal to -1, and L minus L factorial, and L plus L factorial, EL and L. So the pattern equation 5 and 50. There's a syntax. This is first with negative m ML with positive ML relation between this and this. Second one, if X is negative, so that is another relation. If negative X is minus 1, L plus and L and P and L plus. Okay. The most important is also nominative. So orthogonality. Since we are going to use to prove that this eigenspace is orthogonal, right? So this is x cosine theta, theta from 0 to pi, so x from 1 to minus 1, right? So that is all from minus 1 to 1, which is P and L prime. If L is nothing, x dx equal to 2 L plus n factorial and n factorial and 2 L plus 1 and L minus n factorial delta L plus 1. Or that is in term of x, or in term of theta, we just go to this spherical coordinates. That theta is from 0 to pi, right? So sine theta d theta, that is integral, correspond to, do not miss this one. And then P and L cosine theta, prime P and L cosine theta. That equal to this, 2 L plus n L factorial, 2 minus 2 L plus 1 L minus n L factorial, so that is, I want to emphasize here, do not miss this. And a few, the first law, L and ML function, it's C table 5.1, so I do not write down here at the same time. You can refer that table and have some of function about this associated polynomial in case for lower L and M. Now we are going to obtain, so now this we are going to obtain, right? Since the solution is associated Legendre polynomial, then we are going to find the function theta, which is in proportion to this. So we are going to give this normalized constant or coefficient we are going to determine. Right, we are going to try to find this. So how to find this? We're going to use, because this is normalized, right? So we're going to use, because, okay, L, M, L, L, M, L equal to 1, right? It's normalized for the eigenstates of orbital angular momentum. So we have this. Then what we need to do is just substitute, since this L is YL, L. YL and L, right, is this product of the theta and phi. So we're going to substitute here this one in the spherical coordinates. Thus be from 0 to 2 pi is for phi angle. From 0 to pi is theta, which you have that's a d omega, right? D theta. So this together is d omega, right? That is this. And then the integral, so here, let me go down that is the complex conjugate of this YLN, so YL prime, LN prime, and this is theta phi, is YL, ML, theta phi, right? That's equal to 1. That is this, right, in the spherical coordinate. Or in spherical, yes, spherical coordinates. So because this sorry, not equal to, this is equal to, okay, that's the same. All the same, same L, same M, that's equal to 1, right? On the left hand side, we keep continuous, so here, this equal to 0 to 2 pi, and for this part is this function. This one, and this one is here, right? So we have a square root 2 pi, and that is square root 2 pi, not square root 2 pi, so we have a 1 over 2 pi. And exponential I m L minus m L pi d phi. This is an angle for that part. And then for this theta part, sin theta d theta, now we have this, right? CL ML square. Then here, P, okay, ML, L, theta, cosine theta, square. Right, this take is complicated because it's a real function. So this it's a complex conjugate PLM is still itself and multiply itself. So this is square. This square here the coefficient we just keep square, and this one we know that is 0, so that integral is 1, right? So now this is equal to 1, so it disappears. So now only for this, take the constant outside. CL and L square 0 to pi sin theta d. Okay, I already write down over there here. So yeah, this one, right? So here, let's go. This is for L. It's not equal. L prime not equal to L. This equal to 0. So I just use here M L L. Cosine theta is a square d theta, and this one is here, is this term. So that's equal to C equal. After when you see L M L square, and then that is 2L plus ML factorial divided by L plus 1 multiplied L minus ML factorial. So we immediately obtain the constant C L and L. We take square root. Then we want to also multiply a factor, which is very convenient here. So we multiply this factor. And then others I take square root, right? Square root 2L plus 1 and L minus ML factorial. That's factor 2 and L plus ML factorial. Okay, so we obtain this eigenstates of L square. Now let's write down the final. So y L and L as a function theta phi, which is minus 1 and L here. Yes, I have to write down somewhere. If not, but you remember here we have this term, right? We have a square root 2 pi. So square root 1 over 2 pi into here, so we have a 4 pi. 2L plus 1. And then this factorial. L minus M factorial, L plus M factorial. And then the P, L, L, L. Cosine theta exponential I M L. So that is the final solution for the eigenfunction of L square in the spherical coordinates. We use the first method. By analytical method, the way is that when we rewrite this analytical method, we found this is a special standard, or not standard, very special differential equation, which is nothing but associated gender differential equation. So we immediately have the solution. Then we can obtain this. Now we take the second method, is algebra. The algebraic method. Okay. I use L plus minus to help us, and something similar like we obtain, use the same method for this spherical harmonic, right? Now we are going to do this. How to do that? First, we know there are several information here, right? So L plus minus apply this eigenstates of the optical angular momentum L square is in h bar square root L plus 1 minus ML plus minus 1. L plus minus 1, right? We know this. This is a Ricci overloading operator which applied the eigenstates of the L square. We have this. Second, we also know this. In the spherical coordinates, I also already gave you that. In spherical coordinates, the operator is plus minus h bar exponential plus minus I phi. And that partial theta plus minus I cos tangent theta partial. So we are going to use this and try to obtain this eigenstates. This is first, and another information. We know if the L plus apply the L, since ML takes maximum value, then there's no more M value, ML can go over, right? So that means if after this one is equal to 0, right? There are no more states back here, right? If this ML equal to L, so L plus 1 is no such, cannot reach higher, right? So because, and also because this, so we are going to use this one. We are going to, okay. So what we are going to use is, we are going to, we will start from this highest, start from here. So we start from here. Since L, this cat in the spherical coordinate is this one, right? We already give the name spherical harmonic. That's equal to 0. So we are going to start from here and look the left hand side and see how to obtain. Okay, so now this, that means now we are going to substitute this spherical coordinate expression of L plus in this case and apply this. Right. So we are going to find what is this. Suppose we do not know. But we at least we already know this one. We already know Lm. We are going to obtain this theta. Since this one, for the phi, we already know from this solution for the LZ, right? This part we already know. Okay, so now we start here. Now, let's first keep that one, and then YL theta phi is 1 over square root 2 pi. Okay, here, ML equal to L, right? L phi. Okay, so we are going to substitute here. That means, so here we have a plus, right? Plus this L plus is H bar. This takes plus, this also takes plus. I L phi. I phi, sorry, not L. I phi. And the partial theta plus, right here plus. I cotangent theta partial phi, and then apply to these states, right? That's equal to 0. Then now let's do this. So you can see, keep going, so now let's write down this first one. This one. This only work on the theta, does not partial to this phi, right? So this one, I take the constant also in front. This one here, right? So now this do this, if you now keep this one, only do this. So this is exponential L phi partial theta, L partial theta, right? And the second term, let me keep it. So I cotangent theta keep here. Now this is only partial to phi, not theta. So theta, this capital theta L is keep here. Then this one, so that we have I L exponential I L phi, right? That's equal to 0. Now I take this I L phi outside. This also I L phi outside. So this is a h bar exponential I L plus 1 pi square root 2 pi. Okay. So here this is only the partial theta L theta partial theta. This one I have I, this I is a minus, right? Minus L cotangent theta. Theta L equal to 0. If we ask this term equal to 0, so only this term should be equal to 0. This is a multiply, right? So we have, then we are going to solve this one. Equal to L cotangent theta. Right, we're going to solve this. So this one is simple. If we divided the theta L both sides of here, this come to here and this go to here, so you can see. Let's do this. Partial theta L theta and theta L theta. Equal to L, okay. L cotangent theta is cosine theta, sine theta, right? Okay, this is theta. So cosine theta, sine theta, d theta, right? Then you can see here, this cosine theta, d theta is a sine, d sine theta, right? So here, then we have a left-hand side is a log. Right-hand side is L log, right? L log sine theta. And plus some constant, right? Since you here, this is a okay, then we have this expression for theta function L when only M L equal to L. Okay, here I give you theta and theta, which is very simple. I'm going to give us a constant and the sine to the L's power, sine theta to the L's power. So Y L is here, right? No, this in this as I have is equal to CL over square root 2 pi sine L theta E by L. Now we can obtain this coefficient since this the integral, right? say that is equal to 1, right? So we have, on this one you will see here that is 2 pi, so that's this one is equal to CL square 0 to pi sine 2L. Here this L, so L, there are two terms, so 2L, right? 2L plus 1 here, theta, d theta, that's equal to 1. This integral gave us this constant, and I just give you the Aspen constant, which later we can explain why it is like this. Let's take this one, because you take this one is from this integral is has a factor of this, and we add this minus 1 to the nth power is considered it is like even function, odd function, so we make it like that. Okay, so that is the we got obtained the limit case, right? We obtained this, so we are going to start from here and try to find the arbitrary m. So ML is arbitrary number, I mean, not equal to the maximum number of L. How about this state or eigenfunction? So now, this is the first step. We use this plus, use plus, let me obtain. Now, how to obtain the others? We can use minus, right? So each minus we go to minus 1. Then we can have this like a ladder from top to go down, step by step, and we are going to deduce the general formula. So that is the idea. Now I'm going to use L minus applied L. Let's give us H bar L plus 1 minus M L. Sorry, not typing now. Minus M L and L minus 1. And L M go to M L minus 1, right? That is this. So we are going to use this. Start from M L equal to L, so we can apply each time to reduce 1. Apply a second time to reduce 2, right? So we are going to find. Okay, we are going to apply this. Then starting from, again start from M L equal to L. Okay. All right, so now what that means here we have L minus applied by L to give us here, right? So that is like here. H bar L plus 1 minus L, M equal to L, right? L minus 1 and L minus 1. This equals to, here we have L squared plus L. This is a minus L squared plus L. So we have 2L, right? Square root 2L, H bar 2L. So that is we obtained. Okay, now we are going to rewrite. So that we will find some of rewrite some of the interesting relation. Okay, so the right hand side, L minus 1, minus applied by L. I'm going to rewrite is the L minus is this power, L minus 1 applied in L. So L minus L is 0, and then minus 1 became plus 1, right? So they are equivalent. This, if you say this is 1, right? First order of L minus. We can rewrite like this. Okay, right hand side. Right hand side, H bar square multiplied square root 2L by L minus 1. I can rewrite like this. Okay, this is a little challenge. So H bar to the power is L minus 1 power, and that's still equal to H bar itself, right? And then the square root 2L, it is like this. I'm going to write this in terms square root I have a 2L factorial and L minus 1 factorial. Denominator is L plus L minus 1 factorial by L minus 1. Let's see here. So here, L minus L is cancel. Minus 1 minus become 1. So this is 1 factorial is 1. Here is 2L, right? 2L minus 1 factorial is 2L. So that final is 2L, right? This one. But now I rewrite it here because I'm going to, this is a kind of arbitrary m. So this is just cover. That is we are going to find the relation here. This factor. Okay. All right. So now let's keep going. That is for the, from here we have this relation. That means when you summarize, so here I have L to the power is L minus 1. This power apply this by L, it gives us H bar is also L minus 1 power to the square root 2L factorial L minus 1. Okay. Factorial and divided by L plus L minus 1 factorial by L minus 1. So now we have this relation. That is for the one case. If they, oh, this one. Okay, now we are going to apply more. Apply again. So now let us see what kind of, okay, so now, let's see, apply. That means the left-hand side, I apply again, another lowering vector operator. Then here, that's B. Okay, that's B, this lowering operator apply here. The result is here, right? That is this result. So that is H bar square root 2L by L minus 1. Then let's keep the H bar here. So this is H bar square root 2L. Then here, that means this apply to here, right? So we have another H bar for this H bar and square root L plus 1, and now ML here is L minus 1, right? It's ML L minus 1, and then L minus 1 minus 1. And Y is L minus 2. Here. Okay, keep going so that equal to, because the left hand side is I do twice. Now this one is H bar square, right? H bar square root 2L. And second one, square root, you can see here. This is L minus 2, right? L minus 1. So we have L square, still have L square minus subtract. You have L, then this is you will see we have L square and minus 2L minus 3, so minus 3L by plus, right? So you will have actually it's like this. It's 4L minus 2. We have factor 2 here. This one minus this one, right? So, okay. And L minus 2. Or, okay, now I rewrite again. Rewrite in terms of ML. Or let's see this. Rewrite. So first, the L minus y L is L minus is 2, right? The 2 I'm going to write down here, L minus 2. So L cancels, and minus 2 become 2, right? So that is a square. Okay. That is right-hand side. Rewrite like this. Okay. Right-hand side. Right-hand side is this h bar square. Okay. Now square I'm also rewrite like this. Same thing like this. L minus 2. Okay, let me take the first h bar square, and then I take the h bar square over here. 2L 4L minus 2 L minus 2 is, okay, let me S equal here, h bar L minus 2, same here, right? And then here, I'm going to give you the result so you can find here. 2L factorial, L minus 2 factorial, plus L minus 2 factorial, y L minus 2. So now for this one, you will see L minus 2 is 2L minus 2, right? This is 2 factorial. 2L factorial divided by 2L minus 2, we have the numerator is 2L plus minus 1, right? Here. This one is 2L minus 2 factorial, right? This one is 2 factorial. This one, right? Okay, so this one canceled. The remaining part is 2L multiplied 2L minus 1, right? And multiply 2 here. So you can see here, this is 2L in this one, and then you come to here, 4L minus 2, minus this square, right? So I can rewrite by this. And now you can see here. This one and this one. Okay, I follow the same thing. You can do 3 times and more. Then similarly, we will have such conclusion. We have such conclusion is if we apply the L minus 2, which times L minus and L times. Apply this by L is from the maximum, ML, that's equal to, according to this, H bar, L minus ML, right? This is ML. Okay, because this is the same as this one, right? So that means, like I said, each time I can rewrite this is L minus how much time they are going to apply. So that is ML, and then this here, H bar ML, and the square root. Here, 2L factorial will fix here, and this one is L minus ML factorial divided by L plus ML factorial and YL ML. That is the relation we can find from this raising and lowering operator. So now, the next job is try to find what is this. Right? We have not obtained, we only obtained YLL, but this one, now we're going to do how to do that. Since we have this is a relation, now we're going to apply, I erase that. Apply this, okay, I think I erased, but I can rewrite. Apply this, the expression is spherical coordinates, so this is a differential equation. And here, left-hand side is just function, so we can very easily obtain, right? So now, just a reminder, because L minus in the spherical coordinate is minus h bar exponential minus I phi and partial theta minus I cosine theta partial phi. Okay. This we already obtained, right? This one, let's keep CL here, we already obtained CL constant here. So let's just keep it to save time, to not write all the terms, right? Sine here, right? This one. Sine L theta, sine theta to L's power, because it's 2. So we apply to the equation here. Apply this to the left-hand side, and then apply this to the left-hand side. Let's see left-hand side. So here, left-hand side, we have a minus h bar exponential minus I phi partial theta minus I cosine theta partial phi, and YLL is CL over square root 2 pi sine theta to the L's power and exponential I L phi. Let's look at this stuff. We can take those two in front since this is a constant. I cannot move this one, right? Because it's here. I just move this one. This one keep here. CL 2 pi. Now inside this one, we only apply the sine theta, right? So that's L sine L minus 1 theta and the cosine theta, right? And then multiply E by L phi minus. So this first term apply to the theta and keep this phi here. Second one we have to apply first. I cotangent theta, and then this one I keep here sine theta L's power, and then apply this we have I L E by L phi. Then I have L here. This I minus I became plus. I have also L here. I have exponential here. I took that outside, right? So minus h bar. Here I have this. So this x I L minus 1 C L, and I have L, right? So L. Let's take L. Okay, L here. Sine L minus 1. Okay, theta cosine theta minus plus here I minus I plus, right? Here this cosine theta we have a sine theta and cancelled. So again we have a cosine theta sine L minus 1 theta. So that is just twice. So that equal to 2 minus 2 h bar. Okay. Exponential I L minus 1 C L or square root 2 pi L sine L minus 1 theta cosine theta. That is left hand side. Then the right hand side. Okay, right hand side is here, right? So then I just equal to okay. Let's use the derivative formula. Let's use derivative. So here, this is a function for right hand side now. We're going to rewrite this sine theta L minus 1 power in terms of this differential derivative. So now let's look at this one. Because 1 over sine L minus 1 sine theta L minus 1 d sine theta 2 L d cosine theta. Let's look at this term. I keep this first term is here. Oh, sorry. Theta. And now here I replace d sine theta 2L d theta and d theta d cosine theta, right? So this one is 2L sine, okay. 2L sine 2L minus 1 sine theta, and then this cosine theta, and then here this term is this cosine d theta inverse, so that is 1 over minus 1, right? Sine theta. Then we have a negative sign, so negative sign 2L here. This L minus 1, we have also this one, so that is L minus 2 cosine theta. Okay, so this one cancel, right? So this become 2L, and L minus 1, so that is L minus 1 cancel this L, and we have this one, so L minus 1, right? So 2L minus sine L minus 1, sine theta L minus 1, and cosine theta. Okay, then look this term. So you can see here, this one, this is our purpose. We are going to replace this one by this. Then here, so because, so we have L minus applied to the point L. Yes. Okay. That is the first one, right? I think I erased that one, but the L, with this one we have minus 2 h bar CL square root 2 pi L sine theta L minus 1 cosine theta exponential I L minus 1 pi. Let's see, what is I think this right-hand side is this right-hand side is only one case, so I need to equal to, just use this one, equal to, h bar equal to L, right, CL, right, okay. We just want to, okay, let's do, just look this one. Look, this one is, now we have here, side L. Apply, so let us say apply without here. So keep continue here. Okay, keep continue, use that one. This is this is down here. So we have a minus 2h bar, keep here, right? Exponential I L minus 1 CL square root 2 pi. And here, I have a minus 2L, so this is a minus 2L. So you might replace just h bar, this one, and minus 2L sine. Cosine is not 1, is 1 over sine L minus 1 theta d sine theta 2L d cosine theta, right? We just apply this one. Okay, So this is we are working, right? So this one is this here, and this one is here. Then what we obtained, we found it is can we write in this way? Yes. Okay. Now we are going to extend. So that is for let's rewrite. Okay. We rewrite again. Then we can find the relation here. We write the left hand side again. We already read the left hand side is L minus 1, right? Right? Equal to, okay, equal to here. Now I'm going to write down h bar L minus 1. Here I still, and this is, oh sorry. That is an exponential I L minus 1. Then the CL, this is a constant, or square root 2 pi. And here, 1 over sine L minus 1, d sine theta 2. Okay, d L minus 1 sine 2L d cosine theta. So here, what I write is you include the m here. But they are equivalent, right? So this is a 1, is this one, and this, and then here, this from here. This one, this I keep same, right? Everything keep. Yeah, this one I only rewrite the h bar. Right, you write h bar in terms of this one. So that is for the first time, and similarly we can do the same thing. We have L minus to the L minus ML's power applied this time to the YLL. Right, this means here this is ML, apply this equal to, according to this, H bar L minus ML. I just rewrite this one. You can do twice as I did twice here, right? So this case, the goal is try to find this relation here. Yes.
So we're not also raising the d cosine theta to the power?
This is theta is. This one, okay, yes, you're right. Yeah, let's do this. L minus 1. Yes. Great. Thank you. This one also. So here then I follow this and also exponential I and L pi and CL, that is constant. And here 1 over sine theta to the L minus ML power, and d to the order of degree is L minus ML to this, if you want to make this a function, sine theta to L, and the denominator cosine theta e cosine theta to also L minus ML power. Yes. So that is like I said. Now, okay. So that this one. So now we are going to do this is a left-hand side, right? Similarly, the left-hand side. Okay, that's enough. So we have this. Now we know that is equal to this. Okay, let's do left-hand side. And then right-hand side is equal to the left-hand side, right? So we have, now this one is h bar L minus ML exponential I ML pi CL square root 2 pi and 1 over sine theta to L minus ML power. Okay, this is not good, right? So we use this one. Sine theta parentheses L minus ML. That is greater than this. Otherwise, it sometimes is constant. Okay, so d L minus ML. Okay, yeah, this is left hand side. Sine theta L B cosine theta L minus ML is equal to, that is also H bar L minus ML and square root 2L factorial L minus ML factorial L plus ML factorial then by L. L and L. We are going to find this, right? So now we obtain the both sides, this cancel, and the others, we keep it. So finally, our goal we reach using this second algebraic method. So finally, we have this y L and L is equal to, just divided that term to the right hand side. So we have CL, CL square root 2 pi, and then this factorial just change, right? So L plus ML factorial 2L factorial L minus ML factorial. Then exponential I, E, I, and L phi. Then the 1 over sine I think here now I don't know how this, and L theta, and the B L minus M sine theta 2L D cosine theta L minus M. Now we can substitute the CL, this constant inside, so we have minus 1L. We use and 2L factorial L plus ML factorial 2L factorial L minus ML factorial. Just substitute the CL, the constant inside, in this formula. So we have minus ML. Alright, that is the final step we obtain. Okay, so with two methods we have the result. Now the property of this, quickly, since textbook list the properties of the spherical harmonic. So now we call this a spherical harmonic. Function. And that is nothing but the eigenstates of the optimal momentum. So now the properties. First one, this we know that is correspond to this all the eigenstates of the spherical harmonic for all the given L we have 2L plus 1 ML value, right? So they forms the basis. Basis in they form the also normal or normalized. So normal basis. That means completeness for M, L from minus L to L, and L, for giving L, even for the subspace, for giving L, sub over all the possible M, L, is equal to unity operator, right? That is completeness. Another case is orthonormal. There's another look at this term. Theta by the inner product of this one, we can insert this unity operator. And that means sum of all the m L from minus L to L. So you see here, this is a cat, a brass theta phi is L M L. L and log is theta cat theta prime and phi prime, right? That's equivalent. And this one, that means M L from minus L to L. This one is this project is of Y L M, right? M L theta prime. And this one just complex conjugate is Y star L and L theta prime phi prime. So this is another property if we use completeness, and we can find out this one, because these are also, since it's a basis set, right? So that is means if not the same angle is 0, is not same angle phi is 0, that's equal to delta cosine theta minus cosine theta prime. Or the delta cosine is the fact this relation. This is the first property we can find from this, since this basis set is orthonormal, so we have this completeness, then this inner product between these two bases, right? This is in the spherical coordinates, two basis vector, bra and cat. If theta and theta prime, the angle is not same, and that's equivalent to the summation of spherical harmonic function with all the ML value, and that gives us orthogonal. This is important behavior. Second one, it is a complex, so that for giving the harmonic, spherical harmonic function, its complex conjugate is equal to, just depend on the m is even or odd. Number 3, it is the parity. Okay, the parity, right? So that is m theta phi. It's take this r, go to the inverse. That's equivalent to change this r. And I will plot this figure so we can see why this angle between change. And that equal to, by behavior of this spherical harmonic, that equal to minus 1 multiplied here, that is here. So this is r, right? Then the p applied r is go to the r prime, which is equal to negative r, right? That's the parity. This is the parity operator, which always changes the vector from negative. So here we have theta, here is phi, right? So when the r go to the negative, go to this one. This r prime go to negative r. And you will see the angle is just pi, this angle plus pi, right? So that is here. with respect to the next r, this angle is pi minus theta, and this phi is just the half circle, right? So that is this one space. And that gives this relationship. If m equal to 0, if m equal to 0, you just substitute equal to 0, you will see, I just give you the result. You can do from this one, is replace m equal to 0 is very easily, you can obtain that is 2l plus 1 over 4 pi pl cosine theta. Pl is I think the polynomial, right? Is, if you remember this definition, 2l L's power e l d cosine theta to the L's power and cosine squared L minus 1 here. Number 5. For this theta equal to 0 is in case if this the function just along z-axis. For this case, y L and L 0, any function applied is very simple. 2l plus 1, 4 pi delta m 0, m L equal to, so only when m L equal to 0 is non-zero. If m L is non-zero equal to 0. This is because we have this P M L L cos theta equal to 1 if M L equal to 0, 0, M L not equal to 0. So we immediately got this one. And for this function, we have first few L and ML, see the table 5.2. That is list there. So in case we need it, we just take that table to calculate. Fine. Okay, let's do examples, practice. See, so far we have obtained this eigenfunction of L squared. And we have some idea for the property that. So now we can try to apply this function. So here we first know this something. Relation between the spherical coordinate and Cartesian. Since if we use the Cartesian, we need to convert to the sphere coordinate. Cartesian coordinate. Nothing is here. Sine theta cosine phi, we know that is x or r. And sine theta sine phi is y over r, right? And the cosine theta is z over r. That is here. I think I also want to answer the question that then you asked me last time, and I just quickly answered that. I think let's get you this. This is r, right? Z, x, y. So that is this relation. This is r project to x by z. And remember you asked me z is b cosine theta r, and y you give a cosine sine. Remember that? Mm. But this is this one. But we need z height in terms of r height, theta height, and phi height. This is a vector. So r height is this direction, right? And theta height is this direction. And phi height is point to the page. So you are going to consider this is a z height here. you project, you can see it's the components are around r height and theta height. So that's different.
Right.
Okay, yeah, so now we are going to consider this. Now because this, so now let's, if you look at the table, you will see here, y 10 theta phi is equal to square root 3/4 pi cosine theta. Then in terms of the x, y, z, so which one is this one? Right, I have a cosine theta here, so that is equal to, okay. In the Cartesian, instead of theta phi, in the Cartesian space x, y, z, that is square 3/4 pi. I replace cosine theta by this, so the z over r. So now it's the only function z for this one. And then that is the first root, right? So there's two. So one is spherical, another is Cartesian. Now the second one, y1 plus minus 1. So m equal to plus or minus 1. In the spherical coordinates, that is minus plus square root 3/8 pi exponential plus minus I5 and sine theta. If in the Cartesian, let's keep the constant here. Here, this one is cosine phi plus minus I sine phi, right? This exponential. And you can see that is be either x or r or y or r. So and then you can see the sine theta is sine theta here. Then this part is correspond to this one, right? So you can see this is a plus minus. I just quickly. X minus plus minus I y over r. Okay, I think this example now we can do exercises. To practice how to convert this. If give us a function is in Cartesian, we need to convert to the spherical because we know the spherical, the eigenstates. So we can do some of calculation. I don't remember, did I give you homework which associated with like this one? Something like this? The last homework is,
Chapter 5.
if not, then you can do your homework, right? Due on Wednesday. So if I do not do the practice, you can do the homework, right? I don't know. This one is like this. I'm not sure homework, I don't think I gave this. If given function is like this, 2z squared minus x squared minus y squared over r squared plus square 3 over pi xz over r squared. And ask you to find eigenstates of your square. You don't have this one, right? Okay. So we can move this to the Wednesday since the time is over here. Yeah, I just try to make sure I remember the homework has something applied to this, but if not, it's okay. Then you can do yourself. If yes, then you just use, you just use the relation here and try to convert this into the spherical, into this. Then you can do all the remaining. Okay.
I'm saving that one for the exam.
Maybe. Yeah. So you need to practice. It is not hard, right? So just try to convert from spherical, from the Cartesian to spherical. Since we know the spherical is given L and M, that is eigenstates of L squared and Lz. So, and also know how to change L plus minus.
So you said we're not, are we going to cover that one on that example on Wednesday or no?
No. I mean, maybe. He said maybe. I said yes, maybe. No, I will not answer this question, but we are going to do the practice on Wednesday, so that is what I said. Then we go to chapter 6. Yeah, I sent the announcement on Blackboard, right? So the December 12th, all are okay, right? For in-class exam.
What day of the week is that?
That's be Monday.
Okay. What time?
What time? Which time you prefer? Morning?
Afternoon?
Afternoon? Okay, it's fine. Afternoon, which time?
Any time is okay for me, so whatever works for everybody.
So everybody prefer
1 or 2 p.m.
1 or
1
2?
That's fine.
Okay. We still have time. So just give. I need to check with Messi. The room is available. Hopefully
1 p.m. would be good.
1 p.m. Okay, after lunch.
Right.
You have energy.
Yeah.
Yeah. Okay. All right.
Last supper.
We should all get together for lunch.
Yeah. You
Beforehand.
can bring some pizza.
Oh yeah, the most depressing pizza party.
Yeah.
If y'all show out for this
Going.
graduate
Oh, okay.
student appreciation week, we can get whatever type of party we want.
There you go.
But
Show up, leave a note.
go over to the Hutchins building.
I'll be giving away final survival kits on Thursday.
How's that going?
Final survival or
The
The kit.
the kit? What do you mean, how's it going?
Do you have any ideas yet?
To be honest, I didn't know I was putting them together, so I'm glad you said something.
Well, I don't have any ideas either, so happy to collaborate. I've got
Wednesday.
Oh, I'm sorry.
Oh, you're fine.
right there. I've got the pro card because we've got that activated event tonight. So, anyway,
Why did you change orders?
you gonna come up tonight?
I have too much shit to do. I gotta
Is that supposed to be the same?
get done. And we're still waiting to figure out what my student is going to give us. It would be up by today. Today in class, he doesn't know what he's going to assign yet. That has to be done by the end of the week. And it's supposed to be a final project for the class.
Yeah, that's the whole point was the.
So that's supposed to be a final project plus a research paper plus a 15-minute presentation.
That's sadistic.
And he doesn't know what he's going to give us yet.
Very sadistic.
We tried it.
So crazy. I don't understand.
Oh, that up there. That was a.
Well,
a
what do you
an
think
example
would be
question.
good? Because I have to
Start
go to
working on with
program
us and was like,
before tomorrow anyway.
So that's
I
not
mean,
connected
I
to
feel
those
like-
anyway. That's a standalone question.
I feel like the obvious answer, something that includes some kind of like caffeine or sugar or something, kind of like you need energy. What else do people,
What's the question?
what needs to be in a finals survival kit that can reasonably be put together on a budget? So like bribe money for professors isn't an option.
Monster Energy and Cliff Bars.
Cliff bars are not on a budget, but
I forgot I was gonna do that. Everyone gets a Cliff Bar. No,
everybody gets half a Cliff bar.
no, have you seen the? You've seen the mini Cliff Bars? Have you?
Oh yeah, you're right.
Yeah.
That's fair.
So instead of Cliff Bars, Fig Newtons.
You get half an Oreo.
If you want to do the painstaking work, you can go to like either Costco or like Kroger and get
Oh,
one of
sorry,
those like.
in your way.
Like, have you seen those like comically large bags of like the most generic candy ever? You can get like a 10-pound bag of them for like $15 or something like that, and then you just put in the little baggies.
Nice.
Like, I'm just not sure what else to put in there.
Maybe like some index cards.
Mechanical pencil refills.
Cyanide.
A little fake tooth.
A gun.
Okay, too far.
It's the same joke you made.
No, mine was kid friendly.
That's a little.
Cyanide is kid friendly.
When life hurts.
Yeah.
Yeah, Jacob and I were in the PLC at the beginning of the semester. I think it was a news article or some kind of headline that I think you saw, and it was "When life hurts, quit trying" or something like that. And we were like,
Jesus.
God.
I don't know. It's
What are y'all doing
it's on my
tonight?
desk.
Y'all want to come out to this Activate event?
What time is it?
7:30.
Oh, I'll probably die if I
Do you have any signups?
No. Hey, but me and my wife are gonna go. It's gonna be fun. I'm gonna have a good time either way.
Where's
I
it?
don't care.
Where's it at?
It's out in Taylorsville.